Hello everyone, my name is Ayoub bin Sheikhi from the University Sidi Muhammad bin Abdullah, Fez. Today I am pleased to present our work on using pre-trained language models to classify mathematical problems. The main motivation for our work is to demonstrate that you do not always need a large language model to achieve excellent performance. In this study, we show that smaller, compact pre-trained models, when fine-tuned properly, can perform almost as well as much bigger models, like DeepSeek, Math, or Queen, or Lava. This is very important because big models need a lot of computing power and memory, which makes them hard to use in real classrooms or on everyday devices. If smaller models can work well, then it becomes much easier and cheaper to use these IA solution in school and education apps. Traditional, traditional, traditional methods such as keyword matching or sample machine learning often fa- fail because they can't capture the context and deep meaning of math problems. Recently, large language models like DeepSeek and Queen have shown much better results, but they use a lot of resources and are hard to deploy in environments with limited hardware. Our approach centers on fine-tuning smaller and more efficient transformer models to enable the deployment of AI solutions in resource-limited settings like schools and mobile devices. We evaluate four models: Modern Beat, which is compact and adapted for educational contents; Roberta, serving as our standard transformer baseline; the Stillbird, a lighter model optimized via knowledge distillation for better efficiency; and Deberta, an advanced model that excels in contextual understanding. By comparing these models, we aim to balance strong performance with practical hardware requirements, making advanced NLP accessible and scalable in education context. Our dataset, we worked with a dataset from Kaggle competition. It contains over 10,000 math problems, each labeled by topic, such as algebra, geometry, calculus, and number theory, and so on. There are 8 categories in total as mentioned in figure. We improve data quality by cleaning and standardizing the math problem text, removing empty entries, normalizing space, and converting text for model input. To address class imbalance, we used paraphrasing models to create different versions of problems, especially for rare classes. We also substituted keyword with mathematical synonym to increase linguistic diversity while keeping meaning intact. This figure mentioned the category augmented And these steps expanded our dataset and helped the models better generalize to new problems. As a result, our model learned more robustly from a rich and more balanced dataset. And we fine-tuned each model with optimized setting using Optona, which helped us find the best learning rate and the batch size for stable training. Using the Adam W optimizer and a linear scheduler, we trained for 10 epochs with a batch size of 32. During fine-tuning, we adapted the model's output layers for our categories and processed text into token. Validation and regularization methods like early stopping were used to prevent overfitting. And we evaluated our models using the micro F1 score, which calculates the harmonic mean of precision and recall across all classes. This method fairly accounts for class imbalances by considering every prediction equally. It gives us a real measure of overall model accuracy for all types of math problems. Among the models we tested, modern BERT large delivered the highest performance, achieving a macro F1 score of 0.8685. This is an impressive result, especially when compared to other state-of-art models such as the Berta and Distelbert and Roberta, which obtained slightly lower score of 0.8514, 0.8462, 0. and 0.8375, respectively. Despite being more compact and requiring less computational power than some alternative, modern BERT nearly matches or surpasses the result of much larger models. This demonstrates that with careful fine-tuning and optimization, smaller model can be highly effective for specific education tasks like mathematical problem classification, offering an efficient solution for real-world applications in education without sacrificing accuracy. Our results show that you don't always need the biggest language model to get strong performance. Smaller, well-adapted models can work just as well, especially in real classroom settings or on devices with limited computing power. This makes advanced AI tools more accessible for education and everyday use. In conclusion, our results show that lightweight specialized models can classify math problems efficiently and accurately, making AI more accessible for real education settings. In the future, we plan to improve these models using continuous learning and by adding more types of data. And thank you for your attention.